Alright, this is my next video. It's actually the next day, so yeah, I don't think I'm gonna do that though. I don't think I'm gonna be able to like be recording every day or something like that, or like record when I'm gonna read this one. Well, maybe this one because it's on my computer. But like if I'm at work, I'm not really gonna record this one. Maybe I could record it. No one's gonna watch it. So yeah. Anyway, I'm gonna keep studying. I feel like I'm using my notebook now. Anyways. Let's see. Excuse me. The network core. Having examined the endless edge that is not. Fuck data centers. Okay, so if a source end system or a packet switch is sending a packet of L bits over a link with transmission rate of R bits per second, then the time the transmitted packet will be okay. So most packet switches are stored and forward transmission at the input to the links. A store and forward transmission means that the packet switch must receive the entire packet before it can begin to transmit the first bit of the packet onto the outbound link. To explore store and forward transmission in more detail, consider a simple network consisting of two systems connected by a single router, as shown in Figure 1.11. A router will typically have many incident links, since its job is to switch an incoming packet onto the outgoing link. In this example, the router has the rather simple task of transferring a packet from one input link to the only other attached link. In this example, the source has three packets, each consisting of L bits, to send to the destination. At the snapshot of time shown in figure 1.11, the source has been transmitted some of packet 1 and the front of packet 1 has already arrived at the router. Because the router employs a store and forwarding, at this instant of time, the router cannot transmit the bits it has received. Instead, it must first buffer, i.e., store, the packet's bits. Only after the router has received all the packet's bits can it begin to transmit, i.e., forward, the packet onto the outbound link. To gain some insight into store and forward transmission, let's now calculate the amount of time that elapses from when the source begins to send the packet to the destination has received the entire packet. Here we will ignore the propagation delay, the time it takes for the bits to travel across the wire at the near speed of light, which we'll discuss in section 1.4. The source begins to transmit at time 0 at time L divided by R seconds. The source has transmitted the entire packet, and the entire packet has been received and stored at the router since there is no propagation delay. At the time L over R seconds. Since the router has just received the entire packet, it can begin to transmit the packet to the outbound link towards the destination at time 2L divided by R. The router has transmitted the entire packet, and the entire packet has been received by the destination. Thus, the total delay is 2L over R. If the switch is set forward a bit as soon as they arrive without receiving the entire packet, then the total delay will be L over R, since bits are not held up by the router. But as we discussed in section 1.4, routers need to receive, store, and process the entire packet before forwarding. Now let's calculate the amount of time that elapses from the source begins to send the first packet into the destination has received all three packets. As before, at time L over R, the router begins to forward the first packet, but also at time L over R, the source will begin to send the second packet, since it has just finished sending the entire first packet. Thus, at time 2L over R, the destination has received the first packet and the router has received the second packet. Similarly, at time 3L over R, the destination has received the first two packets and the router has received the third packet. Finally, at time 4L over R, the destination has received all three packets. Let's now consider the general case of sending one packet from source to destination over a path consisting of n links, each of rate of R. Thus, there are n minus 1 routers between source and destination. N minus 1 router. Okay. Applying the same logic as above, we see that the n to n delay is n times L over R. Okay, let's think about this. Okay. Which means I don't get it. If n minus one routers between source and destination, routers will be the front, will be this x, right? So we're saying n links each of our. So is this one link and this two links? So there's two links minus one. That will be one router. Okay, I see. Hold on, I just want to see the scoring, the score for. Ooh. So 101, minute 106. We'll see. We'll see. Country. Sorry. Someone sent me a message. My friend sent me a message, but at 10 p.m. Why do you want to do at 10 p.m., bro? It's too late for that. Anyways, queuing delays and packet loss. Each packet switch has multiple links attached to it. For each attached link, the packet switch has an output buffer, also called an output queue, which stores packets that the router is about to send into that link. The output buffers play a key role in packet switching. If an arriving packet needs to be transmitted into a link, but finds the link busy with transmission of another packet, the arriving packet must wait in the output buffer. Thus, in addition to the store and forward delays, packets suffer output buffering queuing delays. These delays are variable and depend on the level of congestion in the network. Since the amount of buffer space is finite, an arriving packet may find that the buffer is completely full with other packets awaiting for transmission. In this case, packet loss will occur. Either the arriving packets or one of the already queued packets will be dropped. Figure 1.12 illustrates a simple packet switch network. As in Figure 1.11, packets are represented by three-dimensional slabs. The width of a slab represents the number of bits in the packet. In this figure, all packets have the same width and hence the same length, Suppose host A and B are sending packets to host E. Host A and B first send their packets along 100 Mbps internet links to the first router. The router then directs these packets to the 15 Mbps link. If during a short interval of time the arrival rate of packets to the router, when converted to bits per second, exceed 15 Mbps, congestion will occur at the router as packets queuing links output buffer before transmitting into the link. For example, if hosts A and B each send a burst of 5 packets back to back at the same time, then most of these packets will spend some time waiting in the queue. The situation is in fact entirely analogous to many common day situations. For example, when we wait in line for the bank teller or wait for the front of a toll booth, we'll examine this queuing delay in more detail in section 1.14. Okay, let's see. Okay, so okay, so the store the store and forward transmission doesn't only have a like sending delay. Okay, okay. Ah, Argentina scored. Whatever. I knew they were gonna win. They already had a fucking red car on them, so like on Switzerland, so whatever. Following tables and writing protocols. I mean, how do I tell how long I've been? 24 minutes? Okay, it's not that much, to be honest. Anyways, forwarding tables and routing protocols. Aerial reset that a router takes a packet arriving on one of its attached communication links and forward and packet another one. It's a test communication link. But how does the router determine which link it should forward the packet onto? Packet forwarding is actually done in different ways in different types of computer networks. Here we'll briefly describe how it is done in the internet. Excuse me. And the internet, every end system has an address called an IP address. When a source end system wants to send a packet to a destination end system, the source includes the destination IP address. Because aquí. Sorry. Hold on, my dog is here. I don't know why my dog is here. Am I able to pause it? I want to stop recording. Just want to pause it. I don't know what my dog wants. I don't know why she's here. I'm back. Like 4 more minutes because I didn't stop it. Anyways. don't know why my dog is here. Well, it's not my dog. It's my sister's dog. But whatever. That's pretty cool. I didn't know. Okay. So, routers know how to send the packets to the correct destination by the packets. Is it a packet? I don't know if that's a packet, but IP address and using the router's forwarding table to send to the most nearby router. All right. Circuit switching. There are two fundamental approaches to moving data through a network of links and switches: circuit switching and packet switching. Having covered packet switching networks in this previous subsection, we turn our attention to circuit switch networks. In circuit switch networks, the resources needed on our path, buffer link transmission rates to provide for communication between end systems are reserved for the duration of the communication session between the end systems. In packet switch networks, the resources are not reserved. A session message uses resources on demand and as consequence may have to wait. That is queue. For access to communication links. As simple analogy, consider two restaurants, one that requires reservation, another that requires reservation or accepts them. For the restaurant that requires reservation, we have to go through the hassle of calling before we leave home. But when we arrive for the restaurant, we can, in principle, immediately be seated and order our meal. For the restaurant that does not require reservation, we don't need to bother for reserve a table. But when we arrive at the restaurant, we may have to wait for a table before we can be seated. Traditional telephones network are an example of circuit switch networks. Consider what happens when one person wants to send information, voice or fax facsimile, faxmail, okay, to another over telephone network. Before the sender can send the information, the network must establish a connection between the sender and the receiver. This is a bona fide connection for which the switches on the path between the sender and receiver maintain connection stay for that connection. In the jargon of telephony, telephony, whatever. This connection is called a circuit. When the network establishes the circuit, it also receives a constant transmission in the network links, representing a fraction of each link's transmission capacity for the duration of the connection. Since a given transmission rate has been served of the sender to receiver connection, the sender can transfer the data to the receiver at the guaranteed constant rate. Circuit switch in this network. The four circuit switches are interconnected by four links. Each of these links has four circuits, so that each link can support four simultaneous connection. The host, for example, PCs and workstation, are each directly connected to one of the switches. When two hosts want to communicate, the network establishes a dedicated end-to-end connection between two hosts. Thus, in order for host A to communicate with host B, the network must first reserve one circuit on each of the two links. In this example, the dedicated end-to-end connection uses the second circuit in the first link and the fourth circuit on the second link. Because each link has four circuits, for each link used by the end-to-end connection, the connection gets 1/4 of the link's total transmission capacity for the duration of the connection. Thus, for example, if the link between adjacent switches has a transmission rate of 1 Mbps, then each of the end-to-end circuit switch connection gets 250 kilobytes per second of dedicated transmission rate. first part, then didn't really understand it. My mom got here. Okay, chat. Bye.